spend pretty much the whole class on solution concepts. I'll see how far down we can go along on this. Probably won't make it all the way through, but see how far we go. So we're going to talk about what a solution concept of a game is. So what does it mean to solve a game? And that's what a solution concept is all about. Talk about that. And then we'll actually look at 5 different ways of solving games. Dominant and iterated removal of dominant strategies, maximum, Nash, correlated. There are actually quite a few other concepts which are not as important. I'll just talk about these 5 concepts. If you include that, it's 5. I don't know how far we'll get through this, and then once we finish this, then the rest of the courses, rest of the material in game theory is really all about mechanism design. So we'll go into mechanism design in quite a bit more detail than over here. So far what we got is understanding of the terminology of a game. You have players, you have actions, you have moves, you have strategies, and strategy profiles. And as we saw last time, things get very messy in real world when you have lots of different kinds of strategies. And in fact, what you do is to just have these toy examples where each person has very, very simple choice of actions, a simple choice of strategies, and we also assume we know the payoffs for all the players. So one of the fundamental concepts in a game is the notion of a solution. So solution means what is the strategy that we expect each player to play. So in other words, given the payoffs, given the rules of the game, what would be a rational player playing? Okay, and so what we do is we put ourselves in the shoes of the players and say, okay, if I were the player and I knew the rules of the game and I knew that the other player is also rational, all the other players are rational, what is it that I can expect to have happen? And that's called the solution or the equilibrium. Okay, so equilibrium means that both players expected to play the solution, the strategy that comes up in the solution. So an example will make this clear in just a minute. Now it turns out that the solution that we come up with depends on the concept. So solution is basically strategy profile chosen by rational players, and by rational I mean utility maximizing players. And it's equal to the equilibrium. It's the same as. Now it turns out that depending on how complex you make the thought process, you can get different solutions. So the same game can be solved and come up with different answers depending on what concept you use. So you can say, well, if I play dominant, it's this. If I play maximum, it's this. If I play Nash, it's this. And we'll see that the same games have different solutions, which of course leaves open the question, so what should you do? Right? What should you do? Because you have a game and you say, well, if you believe everybody else is going to play this concept, this is what the equilibrium will be. But if you change the concept, it's going to be something else. Unfortunately, there's no answer to that. Okay, there is no answer to this question of how do we know that all the other players are also going to be using the same solution concept. It's bad enough that we don't know what their payoffs are, but even worse is that if I have a different solution concept and you have a different solution concept, then we'll end up actually with no solution. It's going to end up in complete chaos. So the assumption that is automatically made in game theory is that everybody agrees to use the same solution concept. Okay, and this will become clear in just a minute. The second thing that happens is that it's possible that the outcome from a solution is not the best outcome. Okay, it may turn out that, and we'll see this again in some examples, that what comes out as an outcome, what the solution says is the outcome, and what every player gets from it is actually pretty bad. Okay, and if they were able to cooperate with each other, they would actually do much better. But in fact, the players are non-cooperative. They're not communicating with each other. Okay, and so again, there's this fairly artificial assumption of non-cooperation. So what we'll see is that non-cooperation can lead to loss of efficiency, or maybe bad outcomes. Basically, is what it comes out. What you would call a lose-lose situation, where both players or all players lose because they're not playing with each other. So it's the opposite of a win-win. All right. So let's take a look at an example of a game and what the solution will look like. So I'm going to look at the capture effect game, which was an example 10. So this is a payoff matrix for a Wi-Fi with the capture effect. So we have two players, row and column, and they represent two stations, and we have this payoff matrix. Okay, and this is the send, don't send, send, don't send. Okay, so what we see with capture effect is that if the column players they send, they always win. They always get 1. And because the row player is going to get -1 because they didn't get any data transmission, and they also wasted energy. They get -1 if they send, and they get 0 if they didn't. So let's see what the solution concept is going to look like over here. What happens over here is the row player is going to sit down and say, wait, the dominant strategy, okay, the best strategy for the column player to play is S. Okay, why would they play anything else, right? If they had something to send, they're going to win. If they send it, obviously they're going to send S. So let me just ignore it and just focus here. And if I focus over here, if I play S, I get -1. If I play D, I get 0. All right, so I'd better play D. So this strategy profile DS then becomes the solution of this game. Okay, that's what I mean, the solution of a game. So a rational row player and a rational column player with this payoff matrix is going to end up with playing DS. Okay, that's the equilibrium value. And the payoff to row is 0, payoff to column is 1. Intuitively, it makes sense. If you have Wi-Fi with capture effect, why would you want to, you're only going to hurt yourself by playing S if you're the row player, and the column player says, I'm going to win all the time, I'd rather send. Why would I not send? So you get this equilibrium right away. So it's a trivial example of a solution, just to illustrate the meaning of what a solution means over here. Any questions about this? Okay, so the other game we looked at was this matching pennies game, and I'm going to just draw the matrix here for a second. So -1, 1, 1. Okay, this is the heads and tails for the row and column player. Now, I stated earlier without proof that the best strategy for each of them is to play 50% head, 50% tail. Okay, and I'm not going to prove it now. I'll prove it in a little bit. But so the solution to this game is going to be the mixed strategy: half head, half tail for here, half head, half tail for there. Okay, intuitively you can see it's dominant because let's say you have a slight preference for heads as a row player. If you have a slight preference for heads and you know that, then the column player is immediately going to start playing T. They play T all the time, in fact. Because even if you play heads 51% of the time, then the column player playing T all the time is going to get 51% of the time they're going to win. And 51% of the time they're going to lose. Right? Because it's a zero-sum game. So even if you have the slightest deviation from the matching 50%, you're going to be worse off. So again, the solution of this game is a mixed strategy, 50% over here. Okay, the practical application of this is penalty kickoffs in football. Okay, so when you have World Cup football, if the games go to overtime, what happens? They're penalty kickoffs, right? So what do you have? You have a goal over here, and then you have the D looks like this, and then you have the guy who's going to shoot either here or there. It's pretty much only all they can do is shoot left or right. And the goalkeeper can either dive to the left or dive to the right. There's not enough time for them to see where the ball is going. They pretty much have to decide up front that they're going to dive left or right, okay, for the most part. So you have to, the kicker is going to have to do, it's exactly matching pennies. If they both go left, okay, the goalkeeper wins, this guy loses. And obviously the row player is the goalkeeper and the column player is the kicker. And you'll see that the right thing to do is to be completely crazy and not have any consistent pattern whatsoever. Toss a coin, keep it hidden, and say, that was heads, I'd better kick to the left. And the goalkeeper tosses the coin and says, I'd better jump to the right. Okay, and this is the best thing for them to do. If there's any pattern possible, the other person will detect it. Okay, so that's matching pennies. Again, you can see that there's a lot of complex analysis you can do and so on and so forth. So we're just getting to the heart of the problem, and that's where the game analysis is interesting. It allows us to identify this for the heart of the game, removing all the extraneous parameters over there. Okay, so this example in particular gives us a certain line of reasoning. Okay, the line of reasoning says okay, if I am going to win no matter what, okay, I'm going to get a very good payoff no matter what, then I should play that. I don't really care, right? If that's the best thing I can do, let me just do it. Why bother even worrying about the other players? It's as if the other players don't exist. Okay, that's the best possible solution, right? If I have a game where my outcome is guaranteed, if I make a certain move, independent of what the other players do, then I should play that. Okay, and if every player has such a move where they have to, if they make the move, their outcome is the best, then that is called a dominant strategy equilibrium. Okay, and that's sort of the easiest equilibrium to think about, because here we don't even need to worry about rationality of the players. The players can be irrational and it still works. Okay, so a dominant strategy equilibrium is where every player plays the dominant strategy. And if you recall, the dominant strategy is one such that the payoff from that strategy is greater than or equal to the payoff from any other strategy for that player. Okay, so let's take an example of the case of the Wi-Fi game with the delay sensitive players. So we had the following matrix. Let me just draw the matrix first. So we had the send, don't send. And we had this Wi-Fi game where if somebody waited, it was very bad. They didn't want to wait because that would, interrupt the quality of their voice call or something like that. So essentially, if you defer, you get -2. If you send and somebody else defers, you get 1. If you both send, you get a collision, it's -1. So in this case, it's better for you to collide than it is for you to defer, because deferral delay is bad. Okay. So in this game over here, let's look at the dominant strategies. If the person plays S, okay, the row player plays S, here gets -1, here gets -2. And here he gets 1, here he gets -2. Okay, so basically S is always better than D. -1 is greater than -2, 1 is greater than -2. So the dominant strategy for the row player is S. No matter what the other person does, okay, just ignoring this, you're going to be better off playing S. And the game is symmetric, so the dominant strategy for column is also S. So the equilibrium in dominant strategies is SS. Okay. Which means they both are going to keep sending, they're going to keep colliding, keep losing data. But, that's what the logic of the game says. That's what you should be doing. Now, it would be better if there was some way for them to observe a flip a coin outside and say, okay, first you go, then I go, then you go, then I go. And then each of them actually in that case will be getting, well, in this case, they'll be getting the mean of 1 and -2. Okay, which is -0.5. All right, so it's still better than this. Okay, so but in this case, of course, we're assuming non-cooperation. And later on, when we study correlated equilibria, we can see how we can improve on dominant strategy by using external correlating devices. Okay, for example, if they agree to do coin flips, then of course things are better, but then that's not allowed in dominant strategy equilibrium. So if you're doing dominant strategy, each of them is going to say, I'm best playing S, and we end up in this bad situation. Okay? Any questions about this over here? So dominant strategy equilibrium is considered to be sort of the gold standard for equilibrium because it may not assure you the best outcome, but at least it is not making too many strong assumptions about other people's rationality. Okay, even if the other player is irrational, basically you can't go bad playing S. So it's probably the best thing that you should be doing. So that's dominant strategy equilibrium. Let's do another one. This is a famous example of what's called the prisoner's dilemma, and it shows up all the time. So let me draw the matrix and tell you what it means. So here's the matrix, or bi-matrix actually as it's called. So we have two prisoners, and they're two different cells, and they can't talk to each other. Okay, the warden comes to them and says, look, I want you to defect. Tell me who committed the crime, because they're both accused of committing particular crime. Now, if the prisoner shows solidarity and says, okay, I'm not going to tell you anything, then they play S, and if they defect, they tell on the other person, they play D. Okay, so what happens? Let's say the role player defects. Okay, if the role player defects, then they get, and the other person shows solidarity. So other person keeps quiet, but you defect. Then what happens is you as a role player get 0. That means you're let out of jail. Otherwise, and the other player gets into jail for 4 years. That's -4. Okay. And if, on the other hand, if you keep quiet, you play S, and the other person defects, then you get -4. You get to put in for 4 years, and the other person gets out. And if both of you are quiet, you both put into prison for 1 year. And if both of you defect, then both are put into prison for 3 years. Okay? So this is the setup. So the warden says, look, if you talk, and the other person doesn't, you're out of here. You're free. On the other hand, if you don't talk, then you might be in prison, you'll be in the S thing, you might be in prison for a year more, depending on if the other person did not talk, and the other person does talk, then you're going to be here 4 years. The other person really hurt you by talking, okay, but if you're not talking, so you should talk, right? So anyways, that's the setup, and now you can play around these numbers a little bit. There's a certain ordering relationship that's important, but the analysis of this game becomes very, very interesting, because you have the following problem. You know that if you talk, okay, so let's say you're over here and you want to compare S versus D. So let's compare the payoffs, okay. So here 0 is better than -1, and -3 is better than -4. So no matter what the warden says, it's better for you to talk. I mean, in other words, it's always good for you to take the defect, right? And symmetrically, in dominant strategy, it's better for the other person to make the same defect. So the strategy you're going to end up with is this: you're both going to spend 3 years in prison. Okay, that's what a rational person is going to do. So the warden comes to the deal. The dominant strategy equilibrium is talk. Okay. However, and this is why it's a dilemma, you know that there is a better way. You know there's a better way, which is for both of you to not talk and take this cell over here. However, you can't trust the other person. The other person is as bad as you, right? After all, you're both prisoners, right? You're not nice, upstanding citizens. You're both kind of thieves or whatever it is. So you say, that guy is really going to rat on me, so I'm going to preemptively rat on him or her, and guess what? They're going to get it in here. So you know there's a better world possible, but you're going, this is heaven and this is hell. Heaven is possible, you're both going to hell. Okay, so this same kind of situation occurs in any resource sharing situation where you have free resource. You have free resource, and actually in spectrum sharing as well. So if you're nice and you let everybody else, play nicely with you, you both win. But if you think the other person is going to be mean to you and push you into here, then you're going to be mean, and you're both going to end up losing. You're going to get much worse than here. Okay, it's also called the tragedy of the commons. Okay, there's a piece of land which nobody owns. The first person who takes that and puts a flag there and says, this is mine, okay, wins. Okay, and the other person gets, in this case, other person gets nothing. So the first person, so you're better off, you both take half the piece of land, you live nicely with each other, but in fact there'll be a war. Okay, because if you both try to plant a flag, you'll have a war. This is peace, so war always wins over peace. Okay, in the dominant strategy equilibrium. So it's not a good place to be in, but that's basically where you end up being. So people have studied it a lot because this is a one-shot game. Okay, one-shot game. So you have a game, you presented the alternatives, you do it once. But remember, in a repeated game, they can change strategies. So now it gets more interesting. So what happens is the warden makes a deal with one of these guys, and they both agree to defect, and they both lose. Okay, now 3 years have passed. Okay, now the warden comes back again and says, here's the second deal, what do you guys want to do? Now, what should you do, right? Maybe you can say, okay, this guy defected, but maybe the outcome of the game is this, and then you are asked again, maybe you can take the prior history into account and do something clever. So what people have done is they set up these tournaments where you submit a program, your strategy profile for strategy for a repeated game, and you play this, and you see over a period of, let's say, 10,000 repeated games, who gets the best score, what strategy wins. And funnily enough, despite a lot of people trying lots of very, very sophisticated algorithms, one strategy wins in repeated games, and that's called tit for tat. And what you do there is, in the first round, you play S. You show solidarity, you don't talk. And after that, if the person defects at any point in time, you just repeat whatever they did the previous time. So first time both played S, they always play S, okay, and that's fine. But if anybody doesn't play S, then they get punished with D, and then you can end up over here. And it turns out that across many, many different strategies, if you play tit for tat, if tit for tat is put against many, many different strategies, basically tit for tat does the best. Okay, so there is a game, there's a book called Prisoner's Dilemma, I can't remember what it's called, Anatomy of Cooperation, something like that. I can't remember the title of the book. But the whole book is about Prisoner's Dilemma and about repeated games and so on and so forth. And they show that this has some, this is basically trust but verify. Ronald Reagan had a famous thing about trust but verify. That's what it is. So you play the good strategy once, and then if it doesn't work out, then you repeat exactly what the previous play was for the other person indefinitely after, then that turns out to be the best move. Okay, but here I'm just trying to illustrate that the dominant strategy, unfortunately, is DD over here. Okay, and just to come back to matching pennies, which we're going to have over here, there you can again show, I will show it later, that the dominant strategy is for both of them to play a mixed strategy of 50% each. So dominant need not be pure, it can be mixed as well. Dominant in this case is half heads and half tails. Okay, any questions about this so far? So the bottom line in dominant strategy is, it's great, however the outcomes may not be great. It's great as a solution concept, it's easy to understand, and it's preferred, but the outcomes may not be the optimal outcomes. You might be able to do better in using other outcomes. Okay. All right. So in mechanism design, for example, we will focus essentially on dominant for this reason, because it is the one which makes the least assumptions about player rationality. So if you can come up with a game where the solution in dominant is also optimal in terms of resource allocation, that is great, because you've got something which is not only the one that is a natural choice, but also it does the best thing. Okay, in the prisoner's dilemma, the allocation is bad with dominant, but then maybe you can choose a game such that the outcomes in dominant are what you want, and that's what you want to do. Ah, I see. Okay, so let me just quickly talk about this and then I'll stop. Let's say that the role player, so if we had this game over here where there isn't a dominant strategy equilibrium if you just look at it, okay, because over here D, for this player, this is worse than this. So this is better than this, but this is worse than that. So D is worse than S. Okay, so there is no dominant strategy for, and similarly S is worse than D. There's no relative ordering for S and D for the role player. So in this game over here, we don't have a dominant strategy equilibrium, right, as such. However, we can do the following. We can put ourselves in the shoes of the role player and say, okay, the role player knows that the column player has a dominant strategy equilibrium. The dominant for the column is S. Okay, so the column is not going to play D. So we can then cross this column out. At this point, D becomes dominant over S. Okay, so in a game where a player can, if any player has a dominant strategy, then what we can do is we can say, we assume that that player will play the dominant strategy and cross out everything else, all the other strategies. That reduces the dimensionality of the game, because now of all the different choices, we're only choosing one. At this point, we may end up with dominant strategy. So this is what's called iterated deletion, because in an n-player game, we can keep doing this. We can say, okay, player 5 is going to play strategy number 20. All right, all the other strategies, let's take it out. Now we can reevaluate for all the other players what is their best strategy. Maybe somebody now has a dominant strategy. Okay, we choose that, we remove all the others. And you keep doing this until we end up with just one cell, and that will be the iterated removal dominant strategy. And again, this makes very little assumptions on rationality. It's saying, okay, if we assume that each player is going to make the dominant move, obviously they should be playing the dominant move, and then at this point we can just work our way down to this one single cell. Okay, so dominant strategy is closely related to this iterated removal, and it turns out that just like I said earlier, dominant doesn't exist for any game. For example, dominant does not exist for this game. Even iterated does not guarantee to be. We cannot guarantee that there will be an iterated removal of strategies that will result in equilibrium, because it may turn out that the game is such that we cannot do that. For example, in matching pennies, there is no such way to remove it. In the symmetric game over there, there is no way to remove any of these. I mean, there is no dominant strategy at all, right? So I can't remove any columns. So this iterated thing doesn't work. The only dominant, there's no dominant pure strategy. I should be more precise. Over here I have a dominant pure over here, and if you have a dominant mix, it gets a little bit more complicated. In this case, the dominant mix actually takes everything. We can't remove anything at all, right? So we don't have anything more to do. Okay, any questions about that? Okay, so let's pause here, and then I'll start with the Maximin strategy training. So it's a sort of incentive for you to send in corrections. It's been the first studied equilibria, and there's a paper by von Neumann in 1928 which actually laid out the concept of Maximin equilibria, and a very important proof, a very important theorem which proved that under certain circumstances, Maximin equilibria always exist. Okay, and we'll come to that in just a minute. But before we do that, I'm going to talk about what the equilibria actually means, and how to compute it. And there's some nice graphical things that go with it as well. So, what is a Maximin strategy? Not an equilibria, just a Maximin strategy. Now, I should point out that some people call it the Max-Min strategy, but von Neumann and early authors in game theory used Maximin, and somehow along the way it got changed to Max-Min. So I'm just using Maximin to be consistent with the older authors. So the Max-Min strategy basically is like this. It's a paranoid player. Okay, the player says, I don't know what the other person is going to do. They could be nuts. Okay, they may be doing something really crazy. What I'm going to do is I'm going to play my strategy such that no matter what the other person plays, I'm guaranteed a particular return. Okay, my payoff is going to be at least something, no matter what the other person plays. Okay, so that's it. So it maximizes the minimum payoff, right? So that's what's called Maximin, right? So maximize the minimum payoff. So you're saying it's a very pessimistic or paranoid view of the world. It's not. It's saying, if I play strategy 1, I could get a very big reward, but if I play strategy 1, I could also get a big, very bad, punishment. Whereas if I play strategy 2, my punishment is small. Okay, my payoff, in the worst case, I cannot be punished too much. So let me play that. So it's the kind of conservative, middle of the road, don't take any risk kind of strategy. That's what Maximin strategy is all about. Okay, inside the box strategy, if that's what you want, not outside the box. Now I should point out that there is a bug in the lecture notes. I just noticed as I was preparing today's lecture, example 17, where it says S and D should be reversed. Let me just write down the game and explain to you what the bug is. So let's go to example 6. This is the Wi-Fi game, and so this is the payoff matrix of the Wi-Fi game, and let's look at the Maximin for this game. So again, this is the game, just a normal Wi-Fi game, but if both people send, they both get -1, if they differ, they get 0 and the other person gets 1. If both differ, they both get 0, right? So 0 means you got nothing, 1 means you made progress, -1 means you tried to send but you lost. It's a fairly reasonable modeling. What's the maximum strategy for this over here? So the way you think about it is like this. Remember that there is no dominant strategy over here for either player, right? Because if you play S, you can go better here, but you're better here. So there's not a dominant strategy equilibrium for each of these players, but the maximum strategy does exist. So let's look at it. If a rho player plays S, okay, then they say, look, I could get as little as -1, or I could get as much as +1. In other words, if I play S, maybe the other person doesn't send, in which case I win big, I get +1, or they do send, in which case I get -1. But if I play D, okay, I get 0 or 0, right? So if I play S, there is a possibility I'll get -1, but if I play D, I'm for sure going to get no worse than 0. So to maximize the minimum payoff, so the minimum payoff over here is -1, and the minimum payoff over here is 0. These are both 0. Your maximum strategy as rho player is to play D, okay, because it maximizes the minimum payoff. And in the notes, the mistake I made was to say that for some reason I wrote S. Maximum strategy for the rho player is D. Please make the correction in the notes. And similarly, by symmetry, the maximum strategy for the column player is also D. So the maximum equilibrium is both play the maximum strategy, and it's DD. Okay. So if you're going to play maximum in this game, they both will differ because this is kind of, they can't get hurt, right? This is the I Am a Rock strategy. For those of you who know the song by Simon and Garfunkel, is the I Am a Rock strategy. If you haven't heard that song, you better go listen to it, because then you'll know what maximum means. Okay. Now it turns out that there is a nice graphical meaning to maximum strategy, and let me explain what it is by considering the following payoff matrix. And this will also illustrate the maximum for mixed strategies. Oops. C1 and C2. And let's look at this over here. 3 minus 3. 1 minus 1. So first of all, notice that this is what's called a zero-sum game. So if whenever column wins, row loses, and they actually get the same value each time, right? So if row gets 2, column loses 2. If row gets 4, column loses 4, etc. So any win or any utility gained by row comes at column's expense and other way around. Okay, no matter, so this is a game of pure competition, right? Anything you get must come because somebody else is losing something. It's like, two kids sharing a piece of cake, right? Any additional crumb of cake for the first child is going to come at the expense of the other child. It's pure competition. Believe me, it's true. Okay. So what we're going to do is we're going to compute the maximum strategies for the row and column players, assuming that these players can in fact play mixed strategies. Okay, so we're going to do that. So how are we going to do this? The way you start analyzing the system when you have a mixed strategy is to, first thing you do is you just say, okay, let's assume that the mixed strategy plays, so with some probability P plays R1, and with some other probability 1 minus P plays R2. Okay, let's just look at the row, and it turns out column can be analyzed simply as the inverse of the row. Whatever row wins, column has got to lose, right? Because it's a zero-sum game, so we don't need to actually analyze column at all. We just need to analyze row. Okay, so with probability P, row plays R1, with probability 1 minus P plays R2. So what's the payoff to row, okay, from playing R1 with probability P? Okay, this is nothing more than P times, right, so if the column can play either C1 or it can play C2, okay, we don't know what C1 is going to get. So it's just going, so if it plays C1 and And okay, I should play R1 probability P and R2 with probability 1 minus P. Okay? So let's say you're playing this particular mixed strategy, P1 minus P, and the column plays C1. Okay? So you're going to get, rho is going to get a payoff of 3P, right, if column plays C1, and 2 times 1 minus P, 3P plus 2 times 1 minus P. Right, if it plays C1, right, or it's going to get 4 times, sorry, P plus 4 times, okay, this is P plus 4 times 1 minus P if column plays C2. Okay, and so we can rewrite this as if column plays C1, then rho the payoff is payoff to rho. It equals P plus 2. That's just simplifying the expression. If it plays C2, payoff to rho is going to be 3P plus 2, this is going to be P plus 2. Okay, so you just simplify, this is, yeah. Did I get this wrong? Or what the heck? Let me see, I should read this. Rho plays C1, it gets 3P plus 2. Right. Column plays C2, it gets 4 minus 3P. Yuck. No wonder. Okay. All right, so those are the, yeah? Is it? Oh, yeah, right. I'm not reading this. I need better glasses. Okay. All right. I can't see this and write at the same time. Anyway, so these are the 2 lines. Okay. Now the row, of course, doesn't know what column is going to do, but it knows something. It knows that the column is going to play a strategy that is going to do what? It's going to minimize row's payoff. Why? Because it's a zero-sum game, right? So here is what we can do. Let's draw a graph like this. And on the x-axis, we're going to write down value of P. That's a mixing value. And what we'll do is we'll draw 2 lines. The first line will be the payoff to rho if column plays C1. And the other one is payoff to rho if column plays C2. It turns out we just have to graph these things. So on the x-axis, so this is like 0.5. This is 1, 2, 3, 4. Well, if column plays C1, the payoff row is P plus 2, so it's going to be 2 going to 3, right? At 1, it's going to be 3, so we get a line like that. And if it's 4 minus 3P, starts at 4 and goes to 1 at 1. So it's 4 going to 1, something like that. So you get something like that. Okay, those are the 2 payoffs, right? 2 row, depending on the strategy for column, right? Now, what this means is like this. If P is between the range, it will actually turn out that this bit intersection point is exactly at 0.5. Okay, that's just the way it's been constructed. So if P is less than 0.5, P is less than 0.5, column can play something like this. Okay, this strategy over here. This is the C2 strategy, the C1 strategy. Column can play C1 if P is if column knew by observation that P was less than 0.5, what would happen is column would play C1 and would hold rho down to a value less than 3. Okay, the value less than whatever the value is over here, which is actually not 3 but 2.5. Okay, it's P plus 2. And if P were greater than 0.5, column could play C2 and would push you down over here. So the point at which the row gets the most, okay, and the column gets the least, is going to be the value of P equals 0.5, at which point it's going to get 2.5, okay, as the payoff. And what is the payoff to column? Minus 2.5, right, because it's a zero-sum game. Whatever row gets, column is going to get the opposite of that. Okay, and you can work out through analysis that, in fact, to get that, column actually has to play a mixed strategy as well, where it plays 0.75 C1 and 0.25 C2. That's, I think, a homework problem for you to look at. But ignoring what column is doing right now, let's just look at the strategy, the structure of the space over here. What's going on is that in the mixing strategy, we're making P, the mixing probability, a variable, okay, because we don't know what to get. And what we find is that as we change the mixing strategy, we get a point at which, over here, rho is going to get the maximum minimum payoff. Okay, the minimum payoff is this line over here. This bold line is the minimum payoff, right? It's going to get as bad as this or as bad as that, depending on C1 and C2 is being played, but maximizes the minimum payoff at this point, so that is the maximum strategy. Now, you just invert it, and that's going to be the columns strategy space. And what it can do is you can say column, it can hold rho down to this value at this point over here. So obviously it's equilibrium for column as well. That's what column should be doing in order to keep rho down to the least possible payoff, because it's a zero-sum game. Okay, and if you take the appropriate space, which is the mixing strategy for row and the mixing strategy for column, P and Q, and you draw this, what you'll find is what's called a saddle-shaped space. Okay, you get these points which are these. So if you draw these, what happens is that the row is trying to always find the highest point in the space, and column is trying to find the lowest point in the space, and they'll end up at this saddle point where any deviation for column will allow row to get more, and it's going to push on the minimum side, and any deviation for row will force it to, will actually give it less than it could get otherwise. So one is trying to minimize, the other is trying to maximize, okay, and the saddle point is where these 2 points are met. Okay, and I didn't have the time to sit down and draw a proper three-dimensional curve with saddle points, but I assume you can imagine what it looks like. Let me see if I can draw a saddle. So a saddle is sort of, I can't even draw it properly. How many of you know what a saddle looks like? Okay, great. So it goes over a horse, right? So it's always the ridge of a horse is the maximum. So row player is the spine of the horse, and then the column player is, it goes like that on. So you're sitting there. So the saddle point, the point in the middle is so the point where the row is maximized and the column is minimized. Okay, and that's the minimax strategy when drawn properly, which I just can't do over here. But the projection over here is what's going on. So we can think of this projection as being just a projection where only P is being considered. We can do a similar projection where Q is being changed, the mixing of the column is being changed along this dimension, and what will happen is that these points will actually fall off like this for the row, and it will actually go like this for the column. Okay, so we want the column to minimize it. So the existence of maximum strategies is the basis of von Neumann's theorem. He showed that essentially, if you have two players, it's a zero-sum game, then we can guarantee that there is a saddle point. Okay, so there is going to be a mixed strategy equilibrium, which is the maximum equilibrium. Now, the dual of maximum is called the minimax. Okay, minimax says, I want to reduce the other player's payoff to the minimum possible. Okay, I don't care whether it hurts me or not, but I want to reduce the other person. Now, in the zero-sum game, it doesn't matter whether you do minimax or maximin, because we're maximizing the minimum payoff. Okay, you're also minimizing the maximum payoff to the other person, right? Because max and min sort of interchange. But we can think of maximum strategy also in non-zero-sum games. And in the non-zero-sum game, maximum strategy just says, this is what the player thinks. Okay, so let's go back to, I'll just draw a matrix over here. We don't need to populate it even. Okay, so let's say you have strategy R1 and R2. So the row player, if the row player is playing minimax, not maximin, row player says, okay, over here the payoff to the other player is something, and here the payoff to the other player is something else. I'm going to be really mean. I'm going to make sure that no matter what the other player plays, I want to make sure that they don't get more than some value. I want to limit the maximum strategy that they're going to get. So you want to limit max of other player, okay, at no cost, regardless of cost to you. And this is the minimax strategy. Okay, minimax says limit the max of the other player, no matter of your own cost. Even if it hurts you very badly to play this strategy, you're going to do that because you want to make sure the other person doesn't get too much. This is the dog in the manger strategy. Okay, it's going to hurt me, but I don't care. The other person is going to get hurt, and that's good. Okay, so I want to find the point where you're going to limit the max of the other player. Okay, that's the minimax strategy. Now, in two-player zero-sum games, there's this nice duality. Minimax and maximin are the same thing. In other multiplayer games and so on, minimax and maximin are not the same thing. And for n players, it's kind of difficult to even describe what minimax means, because a bunch of players have to collude together and mutually agree to hurt each other in order to cause maximum possible harm to the last player left out. Okay, so some kind of collusion going on. So they all gang up and say, let's beat that guy up. It's going to hurt us a lot. We're all going to go to jail. We're going to do it anyway. And so this strategy is not particularly important when you go beyond two-person games. And for two-person games, minimax is the same as maximin. Okay, so we don't need to study that. So let me just quickly recap then what maximin strategy says. Maximin strategy says, regardless of what the other player is going to do, I'm going to assure myself what's called a safety level, that is the minimum payoff. Okay, I'm going to get this payoff no matter what, and I want to find that point which gives me that. This is a pure strategy maximin. In case of mixed strategy maximin, I want to find that mixed strategy value, in the value of P, such that no matter what the other person does, whether they play C1 or C2 or any mixture of C1 and C2, I'm guaranteed a payoff over here of 2.5. Okay, and again in the homework you'll see that you have to prove that for mixtures also this is the peak point. So if you get over here, this value over here, and this is the maximin strategy. Again, it takes a viewpoint, a very dim viewpoint of everybody else. It's saying, no matter what, I'm at least assured so much, and that's your maximin strategy. Okay, and the minimax strategy is for two-player games. It is the same, but for multiplayer games, it says no matter how much harm I take, I'm going to limit the other person. So basically from the role player's perspective, it's going to say, okay, if the other player plays maximin, what should I play so that I get my best payoff? And for two-person games, if you play minimax, the other person is going to play maximin. Okay. Now the theorem from 111 basically says every finite two-person zero-sum. So if these following conditions hold, so we have finite game, that means the number of strategies is finite. It's two-person, and it's a zero-sum game. Then there exists a maximin strategy for both. Okay, and which may, that's it. Basically, this is von Neumann's theorem. And this is existence proof. Okay. All right. So that's all I wanted to talk about maximin. So let me stop here for a minute. So any questions about this? So it's interesting to contrast the minimax with the dominant strategy. So, or maximin or dominant strategy. In the dominant strategy equilibrium, also we don't need to worry about rationality with other players, because you have a dominant strategy. No matter what, that's what you're going to do. In the maximin strategy, the other player is supposed to be maximally punishing you. Okay, and if it's a zero-sum game, it makes sense to play maximin, because in zero-sum game, the advantage you get only comes from the other person's failure. But most games are not zero-sum. right? In the Wi-Fi game, Prisoner's Dilemma game, etc., they're not zero-sum. So we don't actually gain anything by making the other person lose. In a zero-sum game, the only gain you can get is making somebody else lose, but that's not the case for most games. However, historically, a lot of interest was in zero-sum games because, for example, they modeled the Cold War. Okay, every advantage to the U.S. came from the USSR losing something. So that was, there was a clear case of political advantage. You cannot have a win-win situation. So that whole mindset was to analyze zero-sum games. But once that mentality passed away, people have really not focused so much on zero-sum games. They're not as important as they used to be. And the second difference between dominant strategy and maximum is that in dominant strategy, we don't really care what the other person does. We just don't care, right? In the zero-sum game, or even if it's a not zero-sum game, in the maximum strategy, we think that the other player or the other players are actively trying to thwart you. They're actually trying to hold you down. Okay, so it's almost like a malicious opponent. Okay, so normally, as I said, in non-cooperative game theory, we don't think that the opponents are malicious, but in maximum strategy, we think that the opponents are malicious. They're going to do whatever they can to limit you to the worst possible payoff, and then you're going to try and do the best possible you can, assuming your adversaries are malicious. Okay, so that's the difference between dominant and maximum. And again, unfortunately, in games which have both dominant and maximum, they may not match. Okay, so now you say, what do? Right? Should I play dominant or should I play maximum? Well, it sort of depends. If you play dominant strategy, that's basically the best you can hope to do. I guess I should point out that if you have dominant, it's also maximum, right? Because it's getting the best possible no matter what. Well, obviously, that's going to give you the best payoff. But the other way is not true. Maximum need not be dominant. As we saw over here, this has maximum equilibrium, but no dominant equilibrium. Okay. Any questions about this? Okay, let's take a break and then we'll come into the big important equilibrium, which is the Nash equilibrium. Nash equilibria. Okay. So one of the biggest problems in game theory turned out to be what equilibrium should you have? What should you play? And very often people got confused about how each player can start reasoning about the other players. Okay, so you can get into these very complicated tangles where, with Prisoner's Dilemma, for example, you say, well, if I play this, then the other player will play that, therefore I should play that, therefore I should play this, and therefore I should play that. It goes round and round, and it gets really, really messy. Okay, so let's take the Prisoner's Dilemma for the sake of argument. Okay, so I have these two things. I have S and D. N plus minus 1, minus 1, 0, minus 4. Oops, other way around. Minus. So you can say, okay, I'd better play S because there is a good chance the other guy will play S. But if he plays S, it's better for me to play D. But, right, then, so he's going to think I'm going to play D, in which case he's going to play D, right, because he's going to be here, but it's worse for both of them, for both of us, so maybe he will play S, but I mean, it goes round and round. And so all the analyses of games around the late 40s and so on became really this complex thing. It was just horrible. So what Nash did, Nash was a grad student at MIT at that time, and he said, okay, let's assume that that we can choose a particular point in space. Let's argue that there is a point, a cell that all the players know that everybody else is going to play. Okay, let's assume this one. Then all I'm going to show is that it doesn't help to deviate from this, assuming everybody else plays what they're playing. So in other words, let's say that the role player says, okay, this is the potential solution point. Okay, this is potential solution point. Now, that means the column player will play S. Column player will play S. All right. So what you're going to do over here is to say, okay, if I play D over here, Okay, given that the other player is going to play S, if I play D over here, am I going to be better or not? If it pays for me to deviate, then this is not a Nash equilibrium. If it doesn't pay for me to deviate, it is a Nash equilibrium. So let's look at it over here. So if this is the equilibrium over here, if he deviates from S to D, assuming this guy plays over here, is he better off or not? Okay. Huh? He is better off, right? He goes from -1 to 0. So he should deviate, right? So this is not a Nash equilibrium point. Okay? Similarly, if the column player says, if I deviate unilaterally, leaving everybody else in place, I'm going to go from -1 to 0, so I should deviate too. So this is not a Nash equilibrium. But consider this one now. Okay? Let's assume that is a potential Nash equilibrium. Now, if the row player says, okay, if this guy's going to deviate, well, I get -3 here, I get 0 here, okay? So, what's going on? Yes. All right. So if I have this particular spot, so the column is playing D for sure. If I go from here to here, right? I go from -3 to -4. And column, that's worse for me, so I shouldn't deviate. Column player similarly says, I go from -3 to -4, so I shouldn't deviate. So this becomes the Nash equilibrium. Okay, so I just wanted to show you this is not a Nash equilibrium, but this is a Nash equilibrium because unilateral deviation, unilateral means keeping everybody else fixed, deviation does not help me. Okay, now how do I know that this is the chosen point of the Nash equilibrium? How do I know that? I don't. Okay, so that's a big problem with Nash equilibrium. We don't actually know. Now in some circumstances there's exactly one point which has this property, and then we say, okay, then we assume that everybody's going to play Nash and not dominant, and in this case you'll find that this is a Nash equilibrium, but in games which have more than one Nash equilibrium, there is no way to figure it out. Okay, so we'll come to how to deal with that in just a minute. We're going to talk about correlated equilibria, but I just want to get the idea of Nash across. So let's write down the math for that. So we define a new thing. Let's say we have vector strategies S1, S2, and so on until Sn for n players. Then we define S minus I as the vector S1, S2, Si minus 1, Si plus 1, Sn, which means everything except S. And then we can refer to this one as just being the same as Si, S minus I. That's just notation, because the order is not important, right? So this is the same as Si, S minus I is defined to be this, and S1 is defined to be this over here. Okay? So what we say is a Nash equilibrium. Okay, so we say S star, the strategy profile S star is Nash. Okay, if the payoff to the ith person from playing S star, okay, and everybody is playing S minus I, is greater than the payoff or equal to the payoff to the ith playing Si, and other one playing S minus I, for all Si not equal to Si star. Okay, so assuming everybody else plays Si, I guess I should call it S minus I star. Probably that's more consistent. So S star is a Nash equilibrium, and you should probably correct that in the notes as well. I don't know why I left out that star for some reason. Okay, so the payoff from playing my strategy, given everybody else is playing Nash, is as good as or better than playing any other strategy. Okay, that's just it. And this is the standard notation for Nash, so that gives you the Nash concept. And so another way of saying it is basically it doesn't help to deviate. Okay, it doesn't help for me to deviate. Now, so that's the concept over here. Now we can see that this game, Prisoner's Dilemma, had a dominant strategy. It was DD, it was a dominant strategy. It's also the Nash equilibrium. Okay, it turns out that every dominant strategy equilibrium is also a Nash equilibrium. Okay, why is that? Anybody want to? Why is every dominant strategy also Nash? That's right. So dominant strategy is the maximum. You get the best no matter what the other people play. So obviously it doesn't help for you to deviate from there, right? So dominant strategy, everybody is at the best possible. So obviously it doesn't help to deviate. And so trivially it's also Nash equilibrium. Of course the other way is not true. Nash does not mean dominant exists. Okay, so all right. Every maximum equilibrium is also Nash equilibrium. That's again fairly easy to prove, but I'm not going to prove that. Let's instead look at an example of Nash in mixed strategies. So there was a Nash in dominant strategy. Let's look at a Nash in mixed strategy, and we'll go back to our old game, matching pennies. So okay, so this is the matching pennies game. So to do a Nash equilibrium mixed strategies, what we need to do is this. We need to define what the mixing strategy is going to be, okay, for both players, and then we'll show that any deviation is going to be harmful. Okay, that's what we have to show. So how do we come up with the Nash equilibrium? The second problem with Nash equilibria, there's no way to tell what the Nash equilibrium is going to be. Okay, there are some techniques that you can use, some rules of thumb, but generally speaking, we don't know. We have to guess. So intuitively, we guess that the strategy should be 0.5 heads plus 0.5 tails for both. Again, this is based on the analysis of the line of thought earlier. So let's assume we do that. So what we're going to show is that if column plays this, okay, row should play 0.5 head plus 0.5 t. Right? If column plays this, because the Nash strategy is both play half-half mixture, so I'm assuming that column plays half-half mixture. I'm going to show that row should play this. So how do we do this? Basically, we do the same kind of thing that we did earlier. We assume that row plays this with p and this with 1 minus p. Okay? So if column plays half and half, what is the expected payoff? So it turns out, and you can do that the payoff to row, okay, when column plays .5h plus 0.5t, okay, is equal to 0 independent of p. Okay. So if, and you can actually, you can just see just by looking at this, because basically you get -1 or 1, right? So if you're going to get half here, half there, if you play a small amount here and a large amount here, you get more of -1 here, more +1 here, just evens out, more, minus, oh, this is the wrong one, but 1 minus 1. Okay. So you basically, if this is 50-50, then no matter what you play over here, you're going to get the exact same payoff, okay, for the row player, right? So because of this, and because we have a greater than equal to over here, right, I have no incentive to deviate, because it's flat. No matter what p I choose, it's all the same. So 0.5 is just as good as 0.2, 0.8, or 0.7, 0.3, or whatever. So 0.5 is certainly good enough, right? It's not strongly dominant. We don't have a greater than, but we have a greater than equal to. So it's weakly dominant, and so why not, right? Similarly, column player can reason that if row plays this, 0.5 plus 0.5, no matter what column plays, okay, it's going to get a payoff of 0, expected payoff of 0. Okay, again, if row is going to play 0.5, 0.5, column has no problem playing anything. It's going to get the same value anyway. So I chose this because it illustrates a pretty subtle point, which is that what we have over here is greater than equal to. We don't have greater than. It doesn't have to be the best. It just means there's no incentive to deviate. Okay, so that's the funny situation over here. The payoff to row when column plays a half and half mixture is always 0, no matter what p is. So you have to make the assumption that the other person is going to play the Nash. If it is, it doesn't matter what I do. And then we turn that around and say, if I play my Nash, it doesn't matter what the column player does. But of course, it matters that they both play 0.5, 0.5 for the Nash equilibrium. So the line of logic is a bit tricky to follow through, but that's the way it goes. So each person assumes what the other person is going to play Nash and shows that their payoff is greater than or equal to the payoff with any other strategy, right? In our case, S minus I is the value of P. And in fact, over here we have a infinite number of possibilities, but corresponding to P, right? Infinite number of mixed strategies corresponding to P. Okay, any questions about this? Okay, so Nash is not just a pure strategy as I showed over here, but also for mixed strategies. And for mixed strategies, this greater than or equal to becomes non-trivial. Let's look at another game, another Nash equilibrium. This one is called the Battle of the Sexes. And this was defined at a time when it was assumed that men and women had different interests in their entertainment. So you have a husband and a wife, and the husband wants to watch a boxing match, and the wife wants to see ballet. Or F is for fight and B is for ballet. Now, this is 50 years ago. Today we might say either the husband or the wife wants ballet and the other husband or the wife wants to watch a fighting match, because we don't know who wants to watch anything anymore. And some people are politically correct and they say F stands for football and B stands for baseball, and they want to watch football or baseball. All right, so let's look at the game matrix first. So what it says is this: if they both watch the fight, then one player gets 2 because it's the one that they wanted. The other player gets 1 because that's the one that that player did not want, right? So whatever it is, football or fight or whatever, if one goes to the fight and the other person goes to the ballet, they both feel sorry for each other and they both get 0 because they'd rather be together. And same thing over here. And then if this person wins, the column player wins, column player gets 2, and the row player gets only 1 because the row player actually wanted F. Okay, this is an example of what's called a coordination game. Okay, if they choose FP or BF, both of them lose. It's unlike the matching pennies. Okay, so this is an example of a coordination game. So let's look at the Nash equilibria over here. Okay, we'll see that actually there are 3 Nash equilibria. So if this is a Nash equilibrium, okay, why is this a Nash equilibrium? Well, it's obvious it's a Nash equilibrium because if you deviate, it's 0, right? So no matter what you get, even if you get epsilon over here, it's still going to be Nash equilibrium because the alternatives are 0 for both players. Obviously, there's also a Nash equilibrium. Okay? And it turns out there's a third Nash equilibrium, which is a bit harder to find, but 2/3 F plus 1/3 B for the row player, and 1/3 F plus 2/3 B column is also a Nash equilibrium in mixed strategies. And I can you can go through the analysis. It's exactly what I did earlier. You can kind of figure out what the payoff is for each player, assuming. So for this, we'll assume column plays 1/3 F plus 2/3 B, and for some value P, they'll find out what they should be playing. And similarly, they do the same here, and you'll find that this in fact turns out to be a weak Nash equilibrium. In fact, what it turns out is that no matter if the column is going to play 2/3, 1/3 over here, no matter what row plays, they get the same payoff. And if row is playing 2/3, 1/3 like this, no matter what column does, they get the same payoff. Very similar to over there. And therefore, this becomes a mixed strategy, weak Nash equilibrium. Okay? So I just wanted to demonstrate that in this game we have equilibria. Let's ignore the mixed strategy for now and just focus on the pure strategy for a moment. These are both Nash equilibria, right? But which one is going to win? That's why it's the battle of the sexes. We don't know. Okay? And there's no dominant strategy. Okay? There's no iterated removal of dominant strategy. and we can apply. There's no maximum either, because if you play this, you can get 0. If you play this, you get 0. Either way, you can only get 0. So there's no advice coming from maximum either. And Nash says, well, there are 3 different ways you could play. You could guess what the other person is going to do. You could do something, and so Nash doesn't give you much benefit here either. So in these situations, you're kind of stuck. Okay, and there is a way out called correlated equilibria, but I think I'm not going to have time for that. So let me just just a few things about the equilibrium. First thing is that 1951. So what Nash proved was that every game with the finite players and a finite number of actions has at least one Nash equilibrium. Okay, that's a great result. Every game has at least one Nash equilibrium. Okay, you don't know where it is, this existence, but it turns out to be that you can. So it always exists. So how do you find it? Okay, that kind of becomes a problem. So let me explain how to find it in a particular example. In the when you have infinite when you have a certain type of strategy space. So first of all, why is this existence proof? What it uses is something called the Brewer fixed point theorem, and it basically says that if you take a function and you just compute the function on itself, okay, there is a fixed point. It's very similar to taking a matrix, a square matrix, just taking the power of the matrix. You can show that the matrix has a fixed point, sort of corresponding to the eigenvalues. In the same way, any iterated map, any function which can be repeated over is a fixed point. There's some conditions. That's a Brewer fixed point theorem. However, Brewer's fixed point theorem is not constructive. It doesn't say this is what the fixed point is. It just says there must exist a fixed point. So Nash used this. He converted a game into a Brewer type function and showed a fixed point exists. So we're stuck with this situation where we know the Nash, but we sometimes don't know where it is. And in recent years, computer scientists have tried to figure out how hard is it to find a Nash equilibrium. And they've defined a complexity class called PAPD, which because I can't remember, but they've shown the complexity class PAPD includes Nash, and it's pretty hard. So the Nash is going to be. So if somebody says, here's a game, find the Nash equilibrium, it can be quite hard to find. Okay. However, there is one place we do Nash, and say we have the following situation. Let me just use the edges here. If you just sketch, kind of look like this. These. Now, if we had on top of this a surface, okay, surface which was single, okay, and had this one nice point on top, okay, so you have the etch sketch, and one point on the screen, you're told over here, corresponds to the peak, okay, then you know that there's no point for you to deviate from the peak, because that no point, and let's say this peak for both because it's the same. So if this happens, then all you need to do is just find point of optimization, and both players will put their marker over there. It doesn't make sense for deviate. Okay. So in other words, if you have a nice convex space and it becomes dominant, hash out of that for free. Okay. So what this means is that we can do the following. Let's say we have a mapping G that goes from in Rn. Okay, this is the set of actions for the n players. So this is I'll draw that. Okay, and to some payoff vector pi. Okay, which is again a vector of Okay, so I have a set of strategies. We have an n-dimensional etch sketch. So each person has a strategy responds to value in X, and I map this to a vector of payoffs. If we have a convex peak, single peak where they all simultaneously achieve, right? If there's an X star, okay, that the payoff for X star is greater than or equal to the payoff for all X, okay, then what we need simply is to take G and find this optimal point, okay, which is just like optimization problem, and we find that point and we know nobody is going to deviate, and that's dominant and also Nash. So that's one way of Nash in continuous space. So this technique works pretty well for many networking type problems where we can define payoffs, and we can define the payoffs in such a way, single peaked value where everybody does best, and then you say, okay, this is what we're doing, okay, and of course this isn't a pure strategy. Extend the other kind of things to show single peakedness of the overall payoff function in the case of mixed strategies as well. So I'm just going to waving my hands over here about this, but that's generally speaking what you want to do, okay. And there are variants of the Nash game, for example, it's the leader-follower game, or where you have a first person makes a move, the second response, and what they do is iteratively climb until they end up at the peak point, and we can actually show that response to hill climbing. If each move by player slightly improves it, and the structure of the game is such that this peak, they'll actually both end up at the peak here. Of the game over here, but I'm not going to go. Okay. Stop. Quickly review what we did today, and then I'll continue with correlated equilibria on Thursday. Basic solution concept means an equilibrium is going to, and we look at the set of strategy play. That's the solution. That means that you're going to play that part. Everybody plays dominant. That's great. In some games, we can remove dominant strategies for the other players, which will make other strategies dominant. So if you can do that, end up with solution that's removable. Maximum paranoid view of the world. It says the world is out to get me, and no matter how bad the situation is, I guarantee some amount of payoff. I want to max, so that's max. You look at a graphical view. And Nash says, oh, somehow everybody play the Nash equilibrium, okay? And if there are multiple Nash equilibrium, I know somehow that they're going to all play that particular Nash equilibrium, and so I should play mine because it doesn't help me to deviate. So it's much weaker and dominant. But on the other hand, thanks to Nash theorem, it exists at least, whereas the other ones may not. So you have to make a trade-off between existence, and the solution versus and saying, well, I have no idea what to do because no solution exists. And then some of the issues with Nash are solved by the correlated equilibrium we will talk about next time. All right, I'll stop here then.